This is me, Gaurav Jha. Today we are going to talk about the quantum mechanics revision part, and as we will look the start of quantum mechanics and the sudden start of quantum mechanics was not took place. It took a several years, even you can say the time a long period to develop this quantum mechanics. And the start from quantum mechanics was the phenomena where scientists thought and the basic fundamental of quantum mechanics, why people thought that they have to go to the quantum mechanics invention and why it is necessary to develop the quantum mechanics. The first concept comes in the quantum mechanics field is that black body. If you look for quantum mechanics history, you will see they will talk about the black body. And in black body, they generally look for the radiation emitted by the black body because suppose you have a black body, or in case of you can say any metal you have, just for example. And if you heat this metal, means you increase the temperature, then suddenly what will occur? If you place this metal in a dark room where light is not there, then you will realize that after heating at the certain temperature, means if you increase more than 100 or some higher temperature, then you will realize that this body will show some kind of light. That light is called radiation. That radiation, you can say, is kind of radiation emitted by this body, even is a metal. So if I will say this is a metal, so it will emit kind of radiation from itself when you heat it. And generally, it start from some color, like sometimes it start from yellow, red, and then it becomes several colors. So that black body is the you can say what about the black body is kind of a thermal electromagnetic radiation within or surrounding a body in thermodynamics equilibrium with its environment. It is emitted by an idealized object non-reflecting body called black body. So for that, people used to develop the black body, and the concept was is just introduction, rough introduction. Suppose they made this kind of a structure, which was like a spherical section, and here they made some not plane. It's like a rough surfaces where the light will come and it will reflect. Means the starting point from here, light will come and it will come to inside and it will reflect here or there, and it is as much reflection is there, the lot of reflection. You can say multiple reflection will be there, and that will not consider as a outgoing case because the inside is allowed, but the reflection after the entering it will not show the case where light is going to outside. So the all light, the all radiation will absorb in this section sphere, and that sphere will show that light is not coming outside. Means suppose you are looking anything, so how you can see anything? Because the source of light will emit a radiation, a light, and it will go to your eye, from eye to this body, and it will reflect from that body to your eye. Then you are able to see that object. So this is the main concept where you see or you are capable to see anything. That's the cause. Okay, so this was the black body radiation, and here the scientists came and they did some experimental observation. They did that. They just call a graph where this is your energy density UR, and with respect to you can say frequency of a light. So they found a graph. That graph was like this, not this. It was kind of yeah, kind of this, where this was the maximum frequency where the peak occurred. Means at the maximum point of at the point of a certain frequency where the peak of this graph maximum energy density is there, and from that they got some information that this is P. P is kind of power emitted by that black body is directly proportional to the temperature to power 4. And this is Stephen Boltzmann law. Stephen Boltzmann law. And from that, they realized that power and the relation between frequency and the temperature. So nu max, this is your frequency, and it is maximum when it is directly proportional to temperature T to power only one. And this law is known as Weir's displacement law. Wind displacement law. So this two law was the initial case where start of that black body radiation. We start from this these two laws. This was the starting point, and then we got to know that how we approach where the case occurs and how we further go for the case where we will look the quantum mechanics. So from that, one scientist came, and that his name was Rayleigh and Jeans. These were the two scientists, Rayleigh Jeans. These two scientists came and they told that I will do some calculation, I will do some assumptions, and I will make sure that our theory will satisfy the condition, actual condition of black body and energy and radiation, all the things, and they use the formula that is Stephen Boltzmann, this and this Wein displacement law. With the help of this, they thought that with the help of classical mechanics, classical theory, they will be able to explain the black body radiation. So they did further assumption, and then the graph was like this. They further did, and they found that this was the first, second, and third. These are the peaks where, like, you can see further temperature. You can say this is T1, this is T2, and this is T3 on certain temperatures, and this is frequency. So you can say that some frequency nu1, nu2, and nu3. So this type of things are there where the peaks are occurring on the certain frequency, certain nu that occurs by the experimental way. This is kind of experimental data, and that you have to prove by the theory where you can justify your word, whatever you have to prove. So from that they realize, and that the formula I will write simply because here we're not going to do derivation. P T to power 4. This was your Stephen Boltzmann law. From that they realized that P is equal to, and they did some this is Stephen Boltzmann constant sigma T to power 4. And here generally we used to write the sigma value around 5.6 into 10 to power minus 8, and the unit is that Weber per meter square, and per Kelvin power 4, because T to power 4 is there, na, that's the K to power minus 4 will be the reciprocal. So and next is Wien displacement law. From Wien displacement law, what we know that nu max, this is frequency, is directly proportional to what, temperature, and frequency we can say that this is speed of light c by lambda, and lambda because c is your maximum speed of light, so lambda max is directly proportional to t. And further if I do a little bit calculation, so I can say that lambda max means maximum wavelength times temperature, because we did cross multiplication, time temperature is equal to kind of it will be c or b, whatever your choice you can say, but c is like a speed of light that is constant, means this equal to constant. So further, if you do the questions, you can say that lambda 1 T1 is equal to lambda 2. Can say lambda 2 T2. So this is your formula where you will use in a question session if you do question. And from that, you can realize, and that this constant actually, if you calculate that P, you will get approx 2.89 into 10 plus power minus 3 mk for meter and k per Kelvin. Okay, so this is your starting, and then from that further they introduced that classical electromagnetic theory, and further they assume that for the case of cavity, where the cavity of that body occur 1D, 2D, and 3D. There was a different cases from that they used, and they realized that for that condition 2D, 3D, and 1D cavities are there. And from that they realized that how to calculate the average energy. Average energy, they got the formula for average energy was that U T times this was new dependence and where a small period due new. So they got that final 8 pi kT divided by C cube and nu square G nu. So this thing they got from Rayleigh Jeans. That was the initial point where they got the expression, but it was not the as much for from the experimental. Why? Because if you look, this is your experimental value. Okay, this graph is looking like experimentally, but what they got, that was just only a simple parabola because it was satisfying just only a simple a, a case where a certain point means it was not able to follow the whole process where all the experiments is equal to the theoretical position whatever we observe. So this was the failure of religious experiment, and that point that point was not like equal to whatever they did for experimental equal to observation. There's a difference, and that difference was there is justified by Planck's and some other scientists came and Planck's actually they did. And what was the theory behind this justification? Planck actually asked the question. They have doubt that how did you calculate the energy? Because in this case, they are saying that energy is continuous. Energy is continuous. And Planck's doubt on the question, and he asked that how can you say that energy is continuous in this case? Then they realized that energy is not actually continuous. Energy is not continuous. How? Let me write to the case. I will not explain all that, but little bit I will. So d nu is equal to h pi nu square c cube and dv. And this multiplication they wrote kT. KT is what? This is your energy, right? This is your energy. And Planck's actually questions on this point that how you can say that this energy is continuous for the whole process where you did all the observation and your calculation was saying that your energy is constant. It cannot be for that continuous. Maybe sometimes, but where you did this is not the valid case. So he doubted on the points where how energy is constant. Okay, so what Planck did? Planck said that energy is not continuous. Actually, it is discrete. So del E is kT at what point where nu is equal to 0 means nu tend to 0 and energy E is 0 actually when nu tend to infinity. So this was the case where Planck did, and then after Boltzmann distribution occur, and they said that probability. What was the probability? Like you can say, discrete is there. So expectation values were the cases they thought that this is E by kT and divided by kT. This was the case where they asked the probability distribution, and then they find the expectation value of energy, or you can say average value of energy that was from 0 to infinity. E probability of E, you can that energy into probabilities gives you the average energy dE divided by to normalize this we use to this expression value P P and dE. So from that they realize that energy how energy is kind of quanta and zero to E sorry del E del to E like this. This was a continuous energy, not this is a discrete energy, not continuous. They thought that this is a continuous energy system, but it's not continuous. It's a discrete energy. And Planck's did what postulate? Planck's postulate was that this was the discrete energy, not the continuous. Planck's postulate What he told that that energy is like a continuous and it has some relation with this nu. So del E is directly proportional to nu, and from that del E is equal to h nu. That is the Planck's constant and nu. And they didn't know that this is valid for all the system. It further came from the science, Einstein equation. The energy of a photon is h nu. So this is a kind of thing. And Planck did a lot of calculation and he calculated the average energy and then put it on the value. And finally, he got the actual expression. What was the actual expression? Let me write. And that was the actual solution of that black body. And he satisfied that the theory comes and that proved and justified that data which matches with experimental. So UT, nu and du. This was the case where can say UT is the energy density and 8 pi nu square exactly square divided by CQ. So this was the initial case. Here, religions was right, but the KT that was energy, they did much mistake on that point. So Planck's question on that. This is H nu. Nothing that is properly H nu H nu divided by e to power H nu divided by KT minus 1. So this was the actual expression that after religions it came and Planck did this calculation and he found the actual expression and this was the correct achieve and he justified that this energy is continuous uh, from continuous from continuous to discrete you can say. And what was that discrete condition is it said that energy is equal to n h nu means n times of h nu. A single photon or single particle contain the energy of h nu and if you do multiplication like multiple particles are there then it will be equal to n h nu multiple times of particle into one particle contain h nu energy so n times particle contain h nu n into h nu. So this was the Planck's condition. Religions did little bit mistake where energy was the case and then after Planck's justified these conditions where all the things are clear. After saying that energy is discrete condition. So this was the quantum mechanics, the first part. Second, if you say that second thing, that is the great experiment photoelectric effect, Einstein 1905, photoelectric. Photoelectric effect have a lot of significance and it was the first point where Einstein got Nobel Prize for his experiment and that is photoelectric effect. It was the initial start from that it shows that light is kind of particle and the wave nature. It was the clarification where it started, and it gave some justification that light has some particle. It can have kind of different things, but it's kind of particle. So this was the experiment where Einstein did, and what was that? I will give you a rough idea. This is the revision only. So suppose this is your method, and I drop some light. It may be any light so photon or anything it's not like that so after that it will eject some electron after falling the light its electron will come and here concept of kinetic energy maximum yes the is kind of metal surface so here sometimes of experimental observations we do and kind of some so the actual concept is there kinetic energy maximum and where that is like continuously you can say E V naught is kind of stopping potential you can say proportional to frequency so kinetic energy depending on the frequency how much frequency is there Or and you can say that kinetic energy is independent of incident radiation. Incident radiation is not responsible for that, and kinetic energy cases where electron into stopping potential is actually kinetic energy. So this was the photoelectric effect, and further that Einstein did some quantum mechanics concept that from the Planck's constant, he told that his postulate is equal to h nu, and Einstein used the same thing. H is the Planck's constant, and nu is the frequency. And what he did actually photon energy, because if you look for the metal, so here photon is falling and then electron is coming. So photon energy is equal to how you calculate the work function of metal. Work function is of what metal, and plus kinetic energy of electron. Kinetic energy means how much energy is took and how much energy of that electron which is coming out of the metal of electron. Because the electron is coming out and then it has some energy, then because it will leave the metal. So from that photon energy as such h nu we did it. Work function I will write suppose W plus kinetic energy of electron is like kinetic energy maximum, because it may have maximum energy. And work function you can say that is also kind of h nu naught. Nu naught is like a stopping potential means v naught. Okay, so next topic we can write so the value. So kinetic energy maximum you will get here is equal to h nu minus h nu naught. H nu is your energy of photon, and h nu naught like it's a stopping potential. So nu naught you will get is equal to, after substituting the value, h by c into nu minus h by c divided by nu naught. These are the formula where you will use in question solving the photoelectric effect, and you will realize that how you can do these things. Yeah, so this was the starting of quantum mechanics, where you see black body radiation and photoelectric effect. And photoelectric effect is generally kind of that if you for a radiation on a metal, it's kind of a radiation, or you can say a light like photon. Photon is a quantum of packet, right? Photon. What is photon? Photon is kind of packet or quantum of energy. Packet. This contain how much energy? H nu. So this is a photon which contain the energy H nu, and in that case where it is falling on a metal, suppose any radiation or any light is falling on the metal surface, and that metal surface will eject some electron, because metal having some electron in that outermost shell, because uh, it's a metal, so it has some electron, free electrons, so that is called metal. So it electron will come outside. That was the case where Einstein did, and he observed this phenomena, and he got Nobel Prize 1905 in case of year around this section this experiment came. तो आई होप आपको समझ में आया होगा. आई होप यू गॉट दिस. थैंक यू.